let's get this straightened out. So I would like to discuss some recent work we have been doing on weak stimuli that sometimes do and sometimes don't make it into conscious awareness. And I would also like to discuss a few applications of this work that go towards the aim to create a visual prosthesis and interface with the cortex of blind people. But I start with awareness, and I would like you to participate here. So I can't see all of you, but I would like to do a group psychophysics experiment. And so what I'm going to do, I'm going to ask you to look at the dots, and I'm going to present a stimulus around here. And if you see it, raise your hand. If you don't raise your hand. Okay, so 1, 2, 3. Okay, people saw it. Now I'm going to make it more difficult for the more careful viewers. 1, 2, 3. Who saw it? Okay, let's try again. 1, 2, 3. Yeah, that was barely visible. Last time, 1, 2, 3. Okay, maybe some people saw it. Now, I'll be honest with you, there only was a stimulus on the first and on the third. So there were probably a few who responded to the second and the fourth. That is what we call a false alarm. Nothing to be ashamed of, and I'll explain you why. So this situation of detecting weak stimuli has been well described for many years. And a computational psychological theory is the so-called signal detection theory, proposed by Green and Sweats already in the 60s of last century. And what they proposed was that if you are presenting a weak stimulus across trials, there is a distribution of the representation of that signal in the brain. So let's call it the strength of representation. And that has a certain width across trials. So when you present a weak stimulus, sometimes you might get this level of internal stimulus strength. And what you then do is you compare it according to the signal detection theory to a threshold. And if the stimulus is higher than the threshold, then you'd say yes. And that's what we call a hit. If for some reason there's stochasticity in the system, it stays below the threshold, you say no, and that would be called a miss. Now, if there's no stimulus, then you're sampling from a distribution that is shifted to the left. And typically you would stay below the threshold, and that's what we call a correct rejection. And sometimes also because of the noise in the system, you might cross the threshold, and that's what we call a false alarm, sort of a hallucination of a stimulus that was not there. So it's interesting to consider what would happen if I would present to you stronger stimuli. If you then use the same threshold, then you notice that there's still quite a number of false alarms. And it might be a good idea to raise the threshold a bit, because you're going to decrease the number of false alarms. Now you're going to only slightly increase the number of misses, which is just the area under the green curve to the left of the red line. So this is probably a better threshold. But of course, if you use this higher threshold for weak stimuli, you're going to have a lot of misses. So there is this trade-off between the strength of the stimulus and the number of hits and misses that determine where you place the threshold. You can also influence it by, for instance, punishing misses more than punishing false alarms. If you punish misses more, then you're going to have a low threshold. If you're going to punish false alarms more, then you're going to get a higher threshold. So all these things have been described many years ago by the signal detection theory. Now what I want to discuss today is how this maps onto the brain. So where is this internal representation of signal strength? What causes the width of this distribution? So where is this variability coming from? And what is the threshold? Okay, and when we started to collect the data, we quickly realized that what we were studying, it has many links with the so-called global neural workspace theories, or theories of consciousness. So the global neural workspace theory is Bestand de Haane. And these theories propose basically that if you have a weak stimulus, it comes into the cortex, it becomes propagated to high visual areas. And then Stan de Haane proposed that there is this special process that he called ignition that determines whether a stimulus enters into consciousness. And in his theory, this ignition relies on the reciprocal interactions between lower and higher brain areas, such that if you take the stimulus away, there is a memory trace, sort of working memory of the stimulus that you just saw. And if you then present a weak stimulus, two things can happen. The propagation can be so weak that there's no ignition, that would then cause a miss, or it can be strong enough and that will give rise to ignition and therefore a working memory, and that will be a hit. Okay, so we train monkeys on a task that is very similar to what you just did. So on 50% of the trials, they saw a stimulus, and after a delay, supposed to make an eye movement there. On the other 50% of trials, we did not present the stimulus. And on those trials, the monkeys were supposed to make an eye movement to the so-called reject dot that was always there, allowing the monkeys to report that they didn't see it. The monkeys were on the staircase. So we started with high contrast stimuli, and then we gradually decreased the contrast. And at some point, of course, accuracy drops below 80%. So above 80%, we said that is an easy stimulus. Below 80, we said it's of intermediate difficulty. And if it dropped below 40%, we said it's the difficult stimulus. And we recorded from V1, V4 with Utah electrode arrays and also dorsolateral prefrontal cortex with single electrodes. Now, dorsolateral prefrontal cortex is also a brain region involved in the generation of eye movement. So that's also a caveat. We are not going to dissociate the eye movement plan from the conscious perception. So something to keep in mind. Now, when we started the recordings in V1, there was something that I did not expect. I was very surprised by it, and it's shown here. So what you see here is the average activity by low contrast stimuli that are difficult, intermediate contrast stimuli, and easy contrast stimuli. Of course, activity goes up if the stimulus that you present is stronger. But if I then compare the activity listed by the same contrast, so actually this comparison has exactly the same distribution of contrast across trials. Those stimuli that made it into consciousness already had stronger activity at the level of V1 than those that didn't. As if there is variability in the propagation of activity from the retina to the primary visual cortex. Okay. Now it's also interesting to see that the activity on easy miss trials is higher than the activity on difficult hit trials, implying that a certain level of activity in V1 is no guarantee that this stimulus will make it into consciousness. In V4, we got basically the same result. If anything, the difference between hits and misses here is a bit larger. But also in V4, a sort of minimum activity level is no guarantee that you'll make it into consciousness, because you see here, this level gives rise to a hit for a difficult stimulus, but it's still a miss for an easy stimulus. Now, the situation was different in dorsolateral prefrontal cortex. So this could be one of the candidate regions where is this internal representation of signal strength. Because here, whenever the monkey was going to report the stimulus, of course, making an eye movement to the receptive field, as I said, we're not dissociating the eye movement plan from conscious perception, then the activity was high. And whenever the monkey would not report it, it would stay low, even for the easy stimuli. And you see there's still a bit of a ramp of activity, apparently not enough to cause ignition. So here you can put this threshold. And it's interesting that we also recorded from the trials without the stimulus. So we can then compare the correct rejections where there's nothing happening in the receptive field, so activity is always low, except on the false alarm trials, where the monkey is going to make an eye movement towards the receptive field. And then in frontal cortex, you see this ramp of activity actually up to the same level as a scene trial. Okay, so now this ramp may seem a bit surprising, but we suspect that this is related to spontaneous ignitions that happen at different time points. And if you do the average across trials, then you get a gradual ramp, right? So if on every individual trial just ramps up quickly, but that happens at different time points, and you average, you get this slow ramp. Okay, so of all these regions, there's only one region that is a candidate region for the internal representation of signal strength, and that is dorsolateral prefrontal cortex, because there you get strong activity for hits and for false alarms, and weak activity for correct rejections and for misses. Now, this then gives you a hunch that this variation in internal signal strength depends on the efficiency of the feed-forward propagation. That seems to be a stochastic process. Now, some of this is carried by subcortical structures, so you can reach the frontal cortex without ever going to visual cortex, right? You can just bypass it through the thalamus. So we asked the question, is then this variation in propagation, is that related also to cortical propagation? And we did a very simple experiment to test that. So we basically replaced the visual stimulus by an electrical stimulus of primary visual cortex, and we made recordings in area B4, which is a high visual area. So now we don't present a visual stimulus anymore, we just stimulate electrically a group of neurons in primary visual cortex, and we know that it causes a phosphene, an artificial perception of light. And then we play with the currents, and we see that if you start with high currents, of course, at some point, the accuracy drops. So you get something that is a well-behaved psychometric function. Then we do recordings, ensuring that the V4 receptive field, which is larger than the V1 receptive field, overlap. And what you see here is when we give a clearly super threshold stimulus, these are individual trials, and this is multi-unit activity recorded in area B4. So every pulse train that is visible to the monkey causes a visual or an electrical response in area B4. And if we then do the same trick and we compare those trials that are perceived by the monkey to those that are not, we see that, again, for the difficult trials, those that make it into consciousness elicit much more activity in V4 than those that do not. And we also see that a certain level of activity in V4 is no guarantee that the stimulus will make it into consciousness. That's what we saw before. So some of this variation in internal signal strength is really due to cortical propagation that is sometimes apparently more efficient than at other times. Okay, now when I presented these data in a meeting where Stan de Haan was present, he said, oh, this is exactly what I would have predicted. So he did some modeling work on how a stimulus can make it into consciousness. And he said, you know what I'm going to do? I'm going to make the simplest of all models that can explain this. So we're now having a model, but this model has only 5 neurons. So the whole brain is modeled by 5 cells. Okay, and there's one in the LGN. Then there's one in the visual cortex, feed-forward connection. There's a self connection here as well. And then activity goes to V4. There's also a feedback connection, parietal cortex and to frontal cortex. Now, what Stan did, and that was the trick, is to make the connections between parietal and frontal cortex strong, and also the self connections, so that if a certain activity level is reached there, activity becomes self-sustained. Okay, if you then take away the stimulus, there's still a working memory trace of that stimulus, and therefore that would be called a hit. And if you present the same stimulus, but due to the stochasticity, this ignition does not occur, and you take away the stimulus, activity collapses, and that would be a miss. And I'm going to go a bit fast here. Basically, he reproduced all the data, including the pattern of activity on false alarms and correct reaction. False alarms, we cannot really see in the model there. It's always some stochasticity. And if it then reaches this threshold where it becomes self-sustained, of course, then you get an activity level that is indistinguishable from a hit. And this is the modeling data, and this is the neurophysiological data. And we did not tweak all the parameters infinitely. But you see, overall, there's quite a nice match. So a model of 5 neurons can basically explain quite a lot of what's going on in the brain. So some conclusions here. So I talked about the signal detection theory, and I would like to now propose that the variation in internal signal strengths, basically the width of this distribution, reflects the variation in feed-forward processing. Then the threshold for perception is a threshold for producing this self-sustained activity. So basically the threshold for a stimulus to enter into working memory. And I think that's kind of evident that false alarms can be explained by these spontaneous ignitions. Okay, now in the face of time, I think I should move on. So the last
6 minutes.
6 minutes. Okay, I'm good. So I will go quickly through this. So we're now using this this information because we want to create an interface with the visual brain of blind people. We are now focused on primary visual cortex, which has a nice retinotopic map of space. So I already explained that if you stimulate there, a person can also be a person who has been blind for several years will see a dot of light at the corresponding location in the outside visual world where you're stimulating in the retinotopic map. If you then insert 1000 electrodes or more, you can create 1000 phosphenes at different spatial locations. And the idea is to work with it like a matrix board along the highway, right? So you make a pattern on the matrix board by flashing several bulbs, a pattern of bulbs. So the idea is to do the same with intracortical microstimulation. So this is the system that you would need, a camera, a pocket processor that transforms camera images into brain stimulation patterns. You'd like to send them wirelessly to the brain and then stimulate the appropriate cells. So that's all things we want to build. We wanted to test proof of principle, and therefore we implanted 1024 electrodes. So there are 16 Utah electrodes, Utah probes with every probe had 64 electrodes, 8 by 8. We punched them into the visual cortex. So 14 of them were in primary visual cortex, 2 of them were in area B4. These are the receptive fields. So we're not covering the entire visual field, actually only a fraction of one of the quadrants, but still a decent coverage of a part of the visual field. Also in the second monkey. Now we can map these receptive fields with a bar of light. I think many of you know how this works. It's still a nice movie. So here you see the arrays. Of course, this is not visible during the experiment. They're under the skin. And if you then present the bar of light, you get a really nice wave of activity across visual cortex. We want to stimulate, not record here. So this is the same task I've been talking about. But now, again, we replace the visual stimulus with an electrical stimulus. And all these small circles are receptive field centers. The one that is white is the one that we're stimulating. And you see that the monkey can do this for hundreds of electrodes. I mean, we're basically reproducing previous work, but they did not use as many electrodes as we did here. An interesting observation is, and something that also that is of importance, is that every electrode has its own threshold, right? So one electrode you may have to stimulate with 50 microamps before the monkey seizes. Another electrode you may have to only do 10 microamps. So here is for one of these electrodes, the hit rate at function of current level. But it's interesting if you then record from area before, I talked about that before. So if you give a weak stimulus below threshold, you see that it also doesn't elicit as much V4 activity. And the moment you start to come close to the threshold, then suddenly V4 activity increases. And there's a very nice match between the V4 neurometric function and the psychometric function. So it might be possible to use the V4 recordings also in patients maybe in a higher visual area. Because mapping the threshold for one electrode is okay. It takes you 20 trials. But if you have 1,000 electrodes, you don't want to spend 20,000 trials in kind of calibrating your system before you come out of bed. Okay, now I have 2 minutes left, so I'm almost there. One of the big questions was, can you also elicit pattern perception in monkeys, or actually later in blind users? So we trained the monkeys to recognize letters from the alphabet. So these monkeys were not blind. So they trained them, for instance, to recognize the letter D and make an eye movement to the corresponding letter. And then we stimulated the pattern of electrodes, chose those receptive fields that together then formed the outline of a letter, hoping that the monkey would make an eye movement there. And the good news is that also that worked. So here we're trying to elicit the pattern L, letter O. Okay, so the letter itself is done by microstimulation, but the choice menu is actually presented visually on the screen. Okay, so the good news is that it works. There's still a lot of development to be done because the electrodes that we're using now, these Utah electrode arrays, they cause a lot of gliosis. So they stop working after about a year. Maybe you also have this experience. There is, of course, a bit of variability across monkeys. And so this is where I would like to stop. So I think we start to understand what a weak visual stimulus needs to do to reach consciousness, and we can use that information now to build a visual cortical prosthesis. Now, in the face of time, I'm not going to go through all the people, but these are the people who really did the work.